What's up everybody, today we are going to talk about something called Chetaev Instability Theorem. In the previous videos we have talked about Lyapunov theorems, right? And we were using Lyapunov theorems to prove stability. However, when we have a system that we know that it is not stable, right? Of course we can, by looking at the trajectories, using OD45, etc. and we can conclude that this system is not stable. Okay, however, if you like to be more mathy, right, and wanna use some mathematical theorems to prove, right, that system indeed is unstable, and there are some instability theorems for that, and Chetaev is one of them. And okay, first of all, there are 5 main points. 1, neighborhood U of x equilibrium point, and which is the origin here in that problem, right? And we are not going to use that, the U neighborhood, extensively. What is important will be U1 in the second point, right? U1 here. U1 will be the subset of this U neighborhood, right? Here, this is origin. And okay, equilibrium point will be contained in U1, okay, but it can be, at the boundary of U1 too. So it is not necessary we need some open set that contains x equilibrium, and also that open set must be contained in U1. We don't have that type of constraint, okay? So the constraints, or the, I guess, conditions are a little bit more, relaxed compared to the Lyapunov constraints, right, we were dealing with. And in the third one, like in the Lyapunov function case, v must be positive, but for all the x points in U1, okay. And if you wanna, have some type of visualization to, make things a little bit more tangible, this, I guess, bluish looking color region is U1, right? And I didn't wanna draw that, but let me get another color. Okay, this region inside the circle, it is our U, right? There are 2 sets. One is U, which is the neighborhood of our equilibrium point, okay, and but we are not going to use that much. It doesn't have much of a significance other than the definition. And of course x equilibrium will be contained in that neighborhood U, okay. Probably we are going to select as the circle region or volume depending on dimension, okay. 2, we will have U1 set, okay, and which will be the subset of U, okay, and x equilibrium will be contained in U1, but it can be located in the boundary of U1, okay. All right, and third condition, v must be positive, right, for all the x points in U1, okay. Fourth condition, v dot must be, usually what we would say if we were dealing with Lyapunov stability, we will say v dot be negative, right, okay. But now we are trying to prove instability, okay, and so it's reversed in some ways. V dot must be positive, not everywhere, by the way. This is our neighborhood of the open set neighborhood of the x equilibrium, not that type of condition. V dot must be positive in U1, right? And U1 is not an open set neighborhood of X equilibrium. It is subset of U, or subset of open set neighborhood of X equilibrium, and it can contain, right, or it must contain X, and it can contain it on its boundary. Okay, again, conditions are relaxed, not so, these are my conditions. Okay, and fifth condition, v of X must be 0 on the boundaries. Okay, they may look, kind of complicated, or in and of itself, this theorem in this form, right, in this representation, doesn't, make you think about the problems straightforwardly. But now we are going to focus on 3 problems, right? But I should say these are really simple problems, and this can be misleading, right? And to be honest with you, I don't know how we would use this theorem. Of course, by using MATLAB, etc., some type of numerical computation methods. And if we are dealing with 3 or higher dimensional nonlinear dynamical systems, okay, I don't know that. But since second order nonlinear systems are kind of, fundamental to the study of nonlinear dynamical systems, I guess these examples will be sufficient for now. Okay, hopefully in the future I will focus on more about these type of problems. Okay, first problem here, this is the nonlinear dynamical system, second order, x1, x2. Okay, and this is our Lyapunov/Chetaev function. Okay, and by the way, this is the source, and interestingly, unlike Lyapunov, I couldn't find that much of a source only online, right? I mean, I look at the Halil nonlinear systems and nonlinear control book. I mean, so little attention paid to this Chetaev Instability Theorem, and I just wanted to make this clear. I will put this link down in the description, and thank you for, I guess, creator of that website, and that really helped me a lot. Okay, so this is our Chetaev function, all right, and this is our U1, this is our set. Okay, and of course you can look at the definition of the set as well, and I am going to show using MATLAB, right? And this Chetaev function is positive on U1, right? U1, and V dot, we will of course produce or compute V dot, right, analytically, and using MATLAB's symbolic toolbox. Okay, we will then obtain V dot in terms of x1 and x2. Okay, and this V dot will be positive on U1. Okay, and it is like 30 lines of MATLAB code, and considering that I'm not a professional programmer, and you can kind of understand it's not that hard. Okay, especially for that 2D nonlinear systems to pull the instability. Okay, I guess we should go back to MATLAB and look at check the code. Okay, let me use my OBS. Okay, this is problem 1. Again, you can check the nonlinear dynamical system. The dynamics are given here. I am assuming that you are able to see that clearly. Okay, I'm looking at the screen now. It looks okay. And this is our Lyapunov function, or Lyapunov/Chetaev function. Okay, again we need to compute V dot right? And here, this is typical v dot computation. I'm assuming you have watched some videos of mine about the Lyapunov function, and so it should be familiar to you. Okay, this term. All right, by using expand, we can, kind of simplify this expression. Okay, and for example, expand does this. You have in parentheses x1 square or x1 plus x2 right, square. Okay, and it can, yes, expand that expression. Okay, but right, maybe wait a sec, made a mistake. Okay, one sec. Okay, maybe this video has nothing to do with expand or symbolic toolbox, but yeah, wanted to show you nonetheless. Expand, yeah, here you can see squared of the parenthesis term, right? And yeah, it expands that. Okay, it makes it all polynomial. Okay, okay, again, it's like 30 lines of MATLAB code. All right, and here these 3 lines, I mean, I would say that this is a bad practice, right? And this is really, I did it to, okay, let me explain. We have x1 and x2, and x1 and x2 are defined as symbolic terms. Okay, but I want to here you can look at this. I want to plot, right, represent x1 and x2 points, right? There will be points, a set of points, x1 and x2 points. I want to represent them such that v and v dot is positive. Okay, and I mean, I didn't want to clear all the expressions. Okay, I am assuming there are many ways, smarter ways of doing this. Okay, but now I have here v dot, and I also have v, right? No, here v, here is that, and by using char function, okay, and then by replacing this string term with this string term y, this is y x1 underscore vec, because I am going to use that here. Okay, and put x1 underscore vec, right? Put some numerical value for this symbolic value, right? And again, we use replace for that, and do the same for v dot term. Okay, and again, let me run them, right? Wait a sec, what's the issue? Yeah, here char v and char v dot, these are string, like character array. Okay, and you can use eval in, right? Evaluate in base, you can use this function eval in, right? Again, people strongly suggest that you shouldn't use that, or you shouldn't use all the time. This is a bad practice. Okay, and I couldn't figure out a easier way of doing that. Okay, all right, I shouldn't talk much about the programming aspect of it. Yeah, right, after this line, I define x1 and x2, I guess, points, right? And then some x, again I need to have x1 and x2 point, I guess, storage, and I need to record them. I need to record x1 and x2 points, right, such that v is positive, and for all those points v is positive and v dot is positive. Okay, I need to record those x1 and x2 points. Okay, and all right, here, so I just allocated memory for that, you know, filling with zeros. Okay, and okay, for all x1 and x2 points that I'm looking at, compute v for that x1 and x2 point, or let me just say x point. Okay, for that specific x point. Okay, this is a number now. Okay, and again for that x point, compute v dot. Okay, great, and check if v for that x point is positive, and there's n, right, v dot is positive. Okay, if that's the case, right, record that x1 and x2 points. Okay, and then, you know, increment the k iteration constant, okay, variable, and then plot all of the x1 and x points, right, satisfying our, I guess, Chetaev constraints. Okay, all right, so let me run this. Okay, here, this is x1 axis, this is x2 axis. Okay, I am assuming that you are able to see that. Okay, okay, but all right, let me explain again. These red points are the points that satisfy Chetaev constraint. Okay, and here, this first quadrant, right, we can see all the points in the first quadrant satisfy and Chetaev constraints. What are those? Again, v being positive on this set, right, and v dot being positive on this set. Okay, and so we can say this first quadrant region, right, is u1, our u1 set or region, right? Or you can also say here we have another region here, right? Again, it has equivalent point. It has equivalent point. Okay, so red dots are the points where Chetaev conditions are satisfied. Okay, and we can see here two, you know, regions. First is the first quadrant. Okay, and second is the third, like half of the third quadrant. Okay, and we can choose one of those two regions. Okay, because what we are choosing, picking u1, right? u1, we talk about this and we will, you know, look at the other problems as well. u1 must be such that it should, you know, include equivalent points. It can be on the boundary of the u1 equivalent point, and on in all of the points in, you know, contained in u1, Chetaev conditions must be satisfied. Okay, and yeah, we can choose this region or this region, right? Okay, and we can consider this, for example, rectangle region as u, okay, the neighborhood of the equivalent point. Okay, we can, you know, think about that way. All right, this is the first example, right? and we have extensively talked about the coding aspect of it. Okay, I'm assuming you would do that more professionally, and if you do, please let me know on comment section. Okay, all right, so let's check the second problem. Okay, this was the first problem. Okay, and again, source math24.net. okay, so if you think that I'm making a mistake, blame this guy, not me. All right, so here, this is the second problem, and maybe I should do something like that. Okay, this is our nonlinear dynamical system, and this is the Chetaev /real function that we use, and this region is the region that we use. Maybe I should get another color. Yeah, do that, and we can here represent the region like bluish color region, right? U1, and with this given set definition. Okay, and we can see, actually we cannot see at all, but that is what MATLAB is for, right? And we can see, I was going to say we can see v and v dot, they are positive for x in u1. We can obviously see, right? Of course we cannot see that, and we need to use MATLAB for that, right? And okay, so let's go back to MATLAB, and okay, wait, yes, now control up, no, down, yeah, okay, yes, this is second problem, and here we can see the dynamics again, the same, everything is the same, and only these three lines are, yeah, some things that you like to change if you are dealing with other, dynamical systems, or you like to, employ other Chetaev function. Okay, and I did something different, something additionally I did. Okay, this, for example, the lines from 35th to 66th, right? Lines, these are same, right? Of course, those three lines are different, but on top of that, additionally, I also add this like 20 lines of code. For what? For this reason. And for example, first of all, let's run this. Okay, let's run it, then I will explain. Okay, here again we can see the same thing, right? Here, of course, you can, discretize or quantize and more, by using more points, right? Finer discretization scheme you can employ, and it will take longer time, and maybe don't actually, maybe you would, not employ for loops, etc., and you can figure out a way to not, for it to not take a longer time than I'm expecting. Okay, and again we can see that we have two candidates, right? Or we can just, consider these two regions. This is, let's call it region 1, and this call it region 2. Okay, and we can just consider them as one region. Okay, and all right, again, these red points are the points that Chetaev conditions are satisfied, right? So in the problem and in the tablet, right, we look at this region, but again, I'm talking about the general case. You can also, you could also use this region as well, right? You can, construct the set definition of that, region. Okay, so let's close that, because I want to show something else, and let me just Control T. Okay, I just, okay, wait a sec, these codes are totally same. Okay, but only I put this percentage sign. Why? Because I wanted to see the points where v is positive as well. Okay, in blue circles. Okay, I'm going to show you what I mean, right? I'm going to show you what I mean. Okay, here. I feel like you cannot see that though. I mean, or you could have a hard time seeing that. Okay, maybe I should get zoom. Can you see that? I mean, you can clearly see the blue circles, right? But for some points, right, there are red circles, red dots inside of the blue circles. Okay, and I don't know, it might be you like to, visualize that. Again, blue colors are the colors or are the points that v of x is positive, okay, and red points represent the points and where v is positive, right, and v dot is positive. Okay, so that's why the red region is contained in blue region. Okay, all right. But again, I mean, maybe you like to, look at that. Okay, let's go back to our third problem. All right, this was our second problem. Let's look at this third problem. Okay, and here again, this is our make it free. This is our nonlinear dynamical system. Okay, and again, this is Chetaev function, right? And this is our U1 region. Okay, and now we are going to look at if this is satisfied, right? And we need to define, or yeah, we need to in a way construct. We are not constructing in this video, right? We are just checking if the given, I mean, somebody already, for example, somebody gave us this Chetaev function, right? And what we are doing is just to analyze it, whether it's correct, yeah, whether we can use it, or yeah, to prove the instability. Okay, and somebody gave us the Chetaev function, this Chetaev function, and again, somebody also gave us the U1 region. Okay, and we need to look at this. If v is positive on U1, and additionally v dot is positive on U1. Okay, because if it is the case, we can conclude instability. Okay, so let's look at the third problem. Control up. Okay, yeah, here, yeah, there are a couple of Lyapunov or Chetaev functions. Let me just run this again. Wait a sec. Yeah, 30 lines of code or something. Okay, all right. Again, right, in the tablet we use this region, we focus on this region as U1, right? But we could also use this region as well, or we could use the region that is like, you can consider like the union of these two regions. Okay, all right. Okay, again, our same codes, right? Maybe let's check this Lyapunov function or Chetaev function to see if it would work. And no, it's not working, right? We are not able to see some region, right? Okay, so let's use this Chetaev function that we've been using. Or yeah, again, this is not working, right? Or maybe, or let's use this, for example. I wanna, yeah, it's not working. Or maybe this one. Yeah, we can see something. Okay, now we have a some type of region. For example, we can pick this region, right, where x2 is positive, and also we can totally come up with some type of set definition, right? Okay, and all right, I will include these codes, and you can check the GitHub link down in the description. Okay, and at the end here again, I wanna one sec. It's like again 30 lines of code or something. Okay, yeah, here all the things are in this screen. Now you can see that, and here this code you can use it to plot the trajectories, right? Let's look at the problem tree, right? Okay, here wait a sec, let me put it again. Doesn't look very good. Okay, maybe we should wait longer or something. Just plot two trajectories and wait for like 20 seconds. Okay. Alright. I don't know if there's something wrong with that, or wait a sec. Well, now I'm realizing that this system is really problematic, right? Not that it behaves really erratically, right? I am not sure if we are, or it's okay to call that system unstable, right? But it definitely doesn't converge to origin, right? Not that it would blow up, right? Okay, for example, let me run this, and again look at 100 seconds, right? It's really big time, and the black points are the starting initial conditions, and red points are the trajectories, and two trajectories either from that, and but they are not converging to blue, to origin. Okay, and yeah, has some convergence issues. Again, maybe I should do something like this. Let's run it, and it may even look like a stable system as well, and this is like the, I guess, annoying part, but it's not stable. It doesn't come, or asymptotically stable at least. To be honest with you, it is a really pathological case, I feel like. When you first see this, your first instinct, hey, this must be stable, right? But it doesn't converge to origin. Okay, so that was my bad, right? Showing you really pathological case. Let's look at the problem one. Hopefully we won't have that type of issues. Let's look at the trajectories, and my computer is making some noises. Okay, I figure why it was making that noise, my computer. Hopefully you didn't see that. Anyway, and yeah, it's very unstable system, right? And Okay, let's look at this. Let's look at the problem too. Maybe we should, we shouldn't keep the time span very long. This is it. But again, I guess I'm assuming this is a problematic system too. Okay. Okay, I run this. And here we can see some trajectory. This trajectory just going away from the origin. And for that, I feel like we should keep it a little longer. Yeah, okay, that is great. Here, one trajectory looks like it's converging, but these two trajectories are, divergent. Yeah, okay. Again, check the link down in the description, right? And GitHub link. Okay, this code will be, you can, get this code from that link. Okay, and thanks for watching. Don't forget to subscribe, please.